right? Yes.
Yes, sir.
Okay. So it starts with the CAD model, then it follows sequence of steps to get a final part. So this 8 steps are generic process flow chain for any additive manufacturing process. So most of the additive manufacturing process will follow this sequence, same sequence, and these are the steps which you have to follow to complete the physical model. So in additive manufacturing process, first we have to start with the CAD modeling. Whatever the part you want to make, you have to create a CAD model of the required component and save that CAD model into a file format called .stl file. So STL stands for Standard Triangulation Language, or some textbook it is also named as stereolithography file. So you create a CAD model, whatever you want to do, you create a CAD model and save that model in a file format called STL file. Then the third step is part orientation. In the slide I have given two pictures. If you look at the figure of a cat, this is printed in the way in which it is shown. That is, when I print a component layer by layer, first it will print a leg part, then it will move towards the body part, then it will come to print a head. So this is the orientation I can print. In additive manufacturing process, you have a lot of options to orient. It is not like your in conventional manufacturing, according to your design you have to position your component, but in additive, since you are going to add a material layer by layer, any orientation you can keep it for printing. So you have a flexibility of printing a component in all 360-degree in all the axes, all three axes. So it is up to you, but you have to decide the best orientation for part printing. So that is the third step, part orientation. Then based on the way in which you are going to print a part, it is going to generate a support structure. Can you see the right side figure? It is also a printed figure. So as built, the part will look like this. You have a cat at the bottom of the cat, wherever you have a overhanging feature. This is a overhanging feature. Cheek portion is a overhanging feature. Tail bottom is a overhanging feature. So wherever you have a overhanging feature, this will be supported by another material called support structure. So this support structure is required for this orientation. If you tilt a part, then you may require a different type of orientation. So part orientation and the support structure are interdependent. The way you orient, and according to the oriented part and according to the overhanging feature in the oriented part, the support structure will create. So that is the difference between the material. So the solid region is your original model, and the column structure which you can see is a support structure. So here support structure is nothing but where when we construct a building, suppose if you are going for a building construction, ceiling they cannot directly pour a concrete. You all might have seen the building construction. So if you look at the ceiling, before they pour the concrete, they have to create a metal scaffold structure for support. So on the top of the metal scaffold or wooden scaffold, they will put a metal plate. Then over the metal plate, they will pour a concrete and steel. Allow some time for cure it. Then they will remove the scaffold, metal or wood scaffold. So that is what we are doing in construction. Any construction, before you pour a concrete, you need some support. Without support, you cannot pour anything on a three-dimensional space. It is not feasible. Similarly, in additive manufacturing process, as we add a material layer by layer, certain region will take a support from base region. For example, if you look into the top portion of a leg, that particular portion will take a support from the base, because from the base we have a material deposition. But if you look into the overhanging surface, this surface has to deposit a material in based on a CAD model for this particular orientation. It has to deposit a material. But if you try to deposit without support, automatically you will not get a desired shape. So always make sure that wherever you have a sir, wherever you have a support, wherever you require a overhanging feature, make sure that the overhanging feature are supported with a support structure. So that is the fourth step. The fifth step, since the see what I have discussed so far until support structure, it is done in a virtual software. You don't need to create anything on your own. Everything has to be done in a virtual software. And this part is going to be a major part in additive manufacturing process. So I repeat to everyone, you can do a lot of J component work and research work in additive manufacturing from the facility what you have in home or open source software. If you are thorough with this topic, that is second module, data processing, how to process the data for 3D printing or additive manufacturing. So until toolpath, we are going to do it in software itself. So could you able to see this image? No, letter A inside a desktop screen.
Yes, sir.
Yeah. So what is slicing? Because as per our procedure, after part orientation and support structure, we have to slice. Let us take this flow chart. For example, I need to print this cuboid. So I have created a CAD model. I saved the CAD model in STL file format. Since the shape is very simple, whichever the way you orient, there is no issue and there is no overhanging feature. So there is no issue of support structure, right? Then once you are done with the orientation and support structure, you have to slice the CAD model because additive manufacturing process add a material layer by layer. So we have to slice the CAD model into n number of layers. It depends upon machine accuracy. For example, machine is having a capability of printing 0.5 mm. Where thickness of the component is 10 mm, then you have to create 20 slices. That is, virtually you have to cut a part with a plane parallel to XY plane and make sure that between each cut the distance is 0.5 mm. So you will get 20 contour information. So that procedure is called slicing. So that is the next procedure in additive manufacturing. Once you create a slice, for each slice you have to create a tool path. So you require a proper tool path for each slice. So for each slice we have to create a proper tool path. That is, I have one square which is a sliced layer from the cuboid. But how I am going to fill a material within the square perimeter? So I can fill in different strategy. For example, in this case, vertical lines are deposited. I can create a horizontal line. I can create an inclined line. I can create a n number of connected circles. So the way in which you are going to create a material deposition, that is the sixth step, tool path generation. That is the path on which you are going to deposit a material within a given contour. The contour is obtained from a slicing procedure. So this is what the sixth step. Once all these parameters are set, then once all these parameters are set, then you can go for part fabrication. So your physical machine is going to come at step number 7. Then after printing, because after printing you will get a part like this, which I have shown here. So part will have both part as well as support. So using some treatment or some manual or chemical assisted method, you have to remove the support. So that is a post processing. So post processing is to remove the support and to improve the surface finish of a component. So part fabrication and post processing has to be done physically. That is manufacturing part. CAD model to tool path generation, it is completely design part. All your design knowledge you can make use of in any one of this category. So this is the chain in which the data process from virtual to physical in 3D printing process. So this is the data process flow chain, and details of each and everything we'll be discussing in module 2. How to do a CAD model, what are the different method in which you can do a CAD model, what is STL file, what is the uniqueness of STL file, why do you require a STL file for additive manufacturing, what are the other file format we can use it for additive manufacturing. When I go for a part orientation, we have a lot of freedom to do a part orientation, but which part orientation is best? How to select a suitable part orientation for any of the component which you are considering. Then based on the part orientation, we have to create a support structure. But support structure is like a scrap. It is wastage material, but still it has to support your overhanging feature at the time of printing. So you have to optimize the structure. You should use a sufficient material so that it will be stiff enough to withstand the overhanging feature. At the same time, you should not consume much material for support. If it is not, if it is so rigid, then it will be very difficult to remove the support. But at the same time, you need the stiffness to withstand the load. So you have to work on some optimized design. What are the different designs available per support structure? Which design you have to use it for specific application. So those discussion we will discuss in second module. Then slicing, how to do a slicing, what is the minimum layer thickness, slicing depends upon what are the parameter, so what are the different types of slicing available, how the slicing will help you to convert your CAD model into a physical program, because machine is going to run at 7th step, but you have started to create a CAD model as an input data. So how the data is transferred to the machine by using a contouring procedure. So that we will discuss in slicing. Then for each slice, I have identified the contour. That is, I have identified the slice contour for given model. So within the slice, how I have to deposit a material, what is the suitable path is best for considered contour, what are the different path available in softwares, which path I can use it for considered application. So those details we will discuss in module 3, that is module 3. Module 4 is more about part fabrication. Yes, once you define all the parameter in software, we are transferring this data to the machine. So what are the different machines available and uniqueness construction of those machines we will see in module 3. Module 4, after printing, how to remove the support structure, how to enhance the surface finish, how to further improve the property of a material. So that we will discuss in module 4. So this is about the end part of module 1 and introduction part of module 2. If there is any doubt, you just raise a question here, or otherwise we will move to the first topic, CAD modeling, how to do a CAD modeling for additive manufacturing.
Okay.
Yes.
So
Okay.
for support structure, so we need to.
Yeah, just can you give me a second? I'll play one video. I think this video will not have any issue. After the completion of the video, we'll discuss. Just I'll share the video. So I hope no issue in video is visible to you, everyone. There is a turbine blade.
Yes, sir.
Yes.
Yes, I think
Yes,
this
sir.
is some video less memory or less clarity. It is feasible to stream. If there is any issue, stream raise your voice.
Additive manufacturing.
Hello.
So previously your voice was not audible, sir.
Hello. Could you able to hear? Okay.
It's
Now
breaking,
is
sir.
it fine? Audio and video of the. Okay. Now.
The audio is fine, sir.
Okay. Just I'll play this video.
The model is then converted into a triangulated surface mesh.
So in this video, the model which we have taken for explanation is a turbine blade. It is one of the complex component. So first step, what is the first step in additive manufacturing process? You have to create a CAD model. So the CAD model of a turbine blade is done by using some CAD software. Let us say by using Fusion 360, I have created a CAD model of a turbine blade. So virtually I have done with the model. I know what I require, right? Can I proceed to the next step? Any one of you can raise your voice. Can I go to the next step? This is the first step, CAD modeling.
Yes.
Okay. Now, next step is conversion of your CAD model into STL file,
which we call an STL file.
Could you able to see the same turbine blade, but the surface is converted into wireframe model. So I think you all can see this wireframe model, and this wireframe model have connected lines. These lines are nothing but triangular shape lines. Can you see each and every connected line will form a triangle? So this is nothing but a STL file. That is, I'm going to convert a surface into connected patches of triangle. What is STL file? STL file will transfer the data. It will convert your surface data into a line data, and these lines are arranged in such a way that it form a triangular patches and it get connected from one triangle to another triangle. So this how your STL file will look like. Why we require STL file? What is the advantage of STL file? That we will discuss it later. As of now, just understand, yes, there is a file format called STL, and the STL file will look like this. And what is STL? STL is nothing but the connected triangle which follow the same profile of your surface. It is not completely same, but since you have a face sets, there will be a minor error between the surface what you have created and the wireframe model what you have observed here.
STL is now the de facto standard used by all.
So this is the STL file internal view where you can see the connected triangles.
All additive layer manufacturing systems. After inputting the STL.
Okay, any doubt in this until second step? CAD modeling and STL, there are different options available in CAD software to save the CAD model. So one among the format is STL file, STL format. Is it fine? Can you move to the next step?
Yes, sir.
What is the next step? Next step is part orientation. My model is ready and I saved my model in desired format called STL format. Now the third step is part orientation. How I am going to orient a part.
Some additive layer manufacturing systems will automatically generate structures to support overhanging parts of the job.
So let us say I am not going to consider different orientation. I have taken only the particular orientation, and for this particular orientation, if I print layer by layer, this part is downward, this part is upward. So between the part and the table, you have a free space. So directly I cannot deposit a material here. So there is a support structure generation. You can see at the between the turbine blade and the table, there is a light yellow region. This yellow region is nothing but a support required for printing this part at this orientation. If I change the orientation, then I may require a different types of support, different volume of support.
The amount of support structure will depend on both the geometry of the part and the orientation.
For example, if I change a part in this orientation, I have planned that I'm going to take another orientation, and if I print in this orientation
of the part,
support I require, right? So yeah, this is not only two orientation. You can orient a part at any manner you require, but make sure that you are using the best orientation. How to identify the best orientation? That we will discuss in detail. But as of now, know the difference between the two orientation and how this orientation is going to affect the support structure. I think until support structure is clear to everyone, how to orient a part and how to create a support structure. Can I move to the next process, next step?
Sir, here do we use different material for support structure?
No. Okay.
Hello?
Yes. Can you repeat the question? I couldn't hear you properly. Hello?
Sir, I mean like we use different material, right? So like or same material, because if you have to use different material, two different materials has to be deposited
Yes.
based on the design.
Correct.
So what
Correct.
kind
Correct.
of 3D printers will be like will have that?
Yeah. Once we complete this video, I'll come to this point, right? Regarding
sir.
the type of material, right? Okay.
In addition to the amount of support structure needed, part orientation will also affect the surface roughness of the part and the time it takes to build that part in.
So if you look, I have shown here two orientation. Let us say this is first orientation and this is second orientation, right? So first orientation, according to this orientation, this is the support structure I required. And according to the second orientation, the support structure required is shown in the gray, there is light yellow region, right? So can you judge which is the best orientation, first or second?
First one, sir. Maybe.
Yeah, first one. Why first one? Thank you. Why the first one is?
Because a lot of support structures material is being wasted on support structures, sir, and will take more time.
Okay. Correct.
And sir,
Though
the first one is
that
more. The first one is more clearer.
More
clear.
I didn't get you more.
The first one is more clear.
Okay.
Clarity is more in the first one.
Okay.
Yes, sir.
Sir, the second one is better actually, sir.
Why? What is the reason?
Sir, if you see the layer orientation, sir, the overlapping is very high in the second one, sir. So that our surface will be smoother in the second one and it will be kind of rough in the first one, sir.
Correct. Yes. Any other answer? If suppose any answer from others, yes.
Sir, will it be that the first one will have better dimensional accuracy, sir?
Better?
Dimensional accuracy, sir. Dimensional accuracy,
First
sir.
one has. Why? What is the reason?
Sir, because the structure is like horizontal and this is slanting, sir. So while depositing, there might be material flowing or something. Is that possible, sir?
Okay. Correct. Fine. Okay. Anything else other than this?
Sir, I guess the second one is better because the support material and actual product demarcation lines are very specific and clear.
Okay, correct. Okay, thank you. So just as you all mentioned, both first and second, each and first also have certain advantage, second also have certain advantage. So you can see from my cursor. So this I have taken it as a first option, and this I have taken it as a second option. Could you able to see my cursor? Cursor is visible to you?
Yes, sir.
Okay.
Yes,
So
sir.
if you look into the first option, material consumption, that is both part I'm going to print in a same machine. So in terms of processing, there is no difference. Both part I'm going to print in same material. So in terms of material, there is no difference. So in traditional manufacturing process, if you use the same machine and same material, you are expected to get a same output. But in additive manufacturing process, though you are using a same machine, same material, the way in which you orient will have a lot of effect on your functionality. For example, the cost of first printing will be less than the second printing because though I will be consuming the same material for part, but support requirement will be very less. So obviously the cost of first will be less than the second. But if you look into the finish, for example, the inclined surface is shown here. So the closed view of inclined surface is shown here. Here also the closed view of inclined surface. As I deposit a material layer by layer, there is an effect called a staircase effect. So whatever you can see from the video, that is nothing but a staircase. Though it look like a 3D model, when you stack multiple layers, layer by layer, and if it is not following a slope angle of less than 20 degree or greater than 80 degree, because in both axes you have advantage. If the slope angle is less than 20, then you will have advantage in x-axis. If the slope angle is more than 80, you will have advantage in y-axis. But if the slope angle is within 20 to 80, just a range I am giving, but it varies from mission to mission. So that will produce very high staircase. So the first region is giving a high staircase. Because of that, you will be getting very high roughness on the printed part. Whereas in second case, you won't get that roughness. Still, the second part also have a staircase effect, but the roughness value will be less compared to the first case. So that is the difference in terms of what kind of roughness you required. you know the cost which you can spend for the printing. Sometimes you have to do a multi-objective optimization. I need to get a minimum roughness, at the same time I have to reduce the cost. So additive manufacturing gives you the opportunity to do the multi-objective optimization. You can solve the multi-objective optimization. So these are all some of the examples for J component which you can do. For this, you doesn't require any facility. You orient a part, and you can do the orientation and support structure generation in the software, open source software itself. And anyhow, from next class onwards, I'll be teaching that software. So using that, you will be getting a multiple output, and using some multi-objective criteria method, you can optimize the best combination. That is also one of the topic which you can consider for J component, right? So we'll move to the next session, next topic. CAD model is done, part orientation is done. I have supported, CAD modeling is done. I saved that in a STL format, that is a connected triangle. Then later it is oriented in some way, and based on the orientation, support structure is generated. So two examples I have given for orientation. Once the orientation is
The additive layer manufacturing system. Once the part's been orientated and the support structure has been generated,
so let
the
us
resulting
take the first case is best. So based on the first case, the next step is I have to slice the model. That is, three-dimensional model has to be sliced into thin contours. Each and every contour will have a flat layer. So that is what slicing. So this is how the slicing will happen inside the software, but exaggerated view is shown here.
dimensional geometry is then sliced electronically into two-dimensional.
Each slice, it will have a flat face. But when you stack all the variable slice, you will get a 3D component. That is additive 3D printing.
Layers. Each 2D layer representing the profile of a
This data will be sent to the machine layer by layer.
physical layer, which will be made using the additive layer manufacturing system.
You can see each and every slice is a flat face, which has a predefined contour in X and Y axis. Z axis, there is no variation. But when you stack all this, you will get a variable profile for Z axis that became a three-dimensional component.
Once all the layers have been sliced, they're then stored as slice files on the additive layer manufacturing system waiting to be used.
Each slice, you have to define a path in which you are going to deposit a material. That is a sixth step.
On completion, the slice files are then sent to the additive layer
So
manufacturing
when you
system one by one.
When you pack the
where they're
slice,
reconstructed from the bottom up,
you can see from the video,
into a
each and every slice is a flat face. But if you look at the bottom, when you stack the flat face sequential manner, you could able to achieve the three-dimensional profile.
solid three-dimensional part. This process could be done using laser sintering, selective laser melting, stereolithography, 3D printing, fused deposition modeling, or a whole range of different additive layer manufacturing technologies.
Okay, so I hope there is